Hi, today we're going to continue our discussion of antiderivatives, but we're going to talk about their applications in physics. Now, I struggled with physics in high school, but I didn't understand the calculus behind it. Once I started understanding the calculus behind physics, it was really helpful for me. So let's start off with some things that we know. If we're given the position function, we can write that as s of t. Taking the derivative of position, we get velocity. Oops, can't spell velocity right. V of t. Take the derivative of velocity, we get acceleration. A of t. And of course, if you take the derivative of acceleration, you get the jerk, right? Now, going in this direction, we're taking a derivative. So if I want to get velocity, I take the derivative of position. But what if I'm given velocity and I want to find position? I'm going in the opposite direction. Well, what is the opposite of the derivative? The antiderivative. Matter of fact, most physicists do the antiderivative, not the derivative. If I know the acceleration, I can find position. And we're going to see an example like that today, okay? All right, so let's say an example here. The velocity of a particle is given by 1.5 root t. At t equals 4, the position is 10. Find the acceleration and the position functions. So let's deal with the acceleration function, Now, I know if I'm given velocity, to get acceleration, I take the derivative. So acceleration is the derivative of velocity. And I can do this. This is just 1.5 t to the 1/2. This becomes 1.5 over 2 t to the 1/2. Remember, if I take the derivative, I get 1.5 times 1/2 t to the negative half. You can verify that. And then to find the acceleration at 4, I just plug it in. 1.5 over 2 times 4 to the 1/2, which is just 1.5 over 8. Now, they didn't give us any units, so I'm not going to worry about units there. But now we want to find the position. This is where it gets a little bit trickier for us. If I'm given velocity, I want to find position, we have to take the antiderivative. So to get position, s of t, I have to integrate my velocity, t to the 1/2 dt. Now remember, they're not going to tell you to put this dt here, but we need to have it. But let's talk a little bit about why it's so important. Let's think velocity. If this is velocity, that's going to be something like meters per second. dt is our change in time. Seconds. That's what I mean. Remember, the d stands for change, the t, of course, time when you're dealing with physics. When I multiply, those two cancels, and what I'm left with is meters. Meters is a position variable for us. So setting up the integral kind of helps us decide what the values are going to be and what they actually mean. For this case right here, because my units cancel, we get meters. I know that this is going to be a position problem. I'm going to get a change in position for us. So, but when I integrate this now, remember, we're going to add 1. We're going to get 1.5 t to the 3/2 over 3/2 plus c1. And I'm going to rewrite this. We will get s of t equals, now if I flip it, I'm going to get 3 over 3, or just t to the 3/2 plus c1. Now that's not unique. I still have to find c1. And to do this, they gave me the condition. At t equals 4, the particle's position is 10. So they give me the condition x is 10 when t is 4. I can use that to solve it. So now notice they use x. What letter did I use? S. It's fine. 10 equals 4 to the 3/2 plus c1. I just plug it in right there. And if I do this, this becomes 2 cubed, square root of 4 is 2 cubed, 8 plus c1. C1 is 2. So my position function is s of t equals t to the 3/2 plus 2. Okay, go to part 3 and we're going to take a look at acceleration.